All right, I want to talk now about the concept of dB. Now, I always use the example of temperature to kind of explain why in some engineering fields we have all these different units. And the reason is let's take temperature for example. We have the Celsius scale and we have the Fahrenheit scale. And so the Celsius scale is based upon water, right? 0 is freezing, 100 is boiling. The Fahrenheit scale, I don't know if you knew this, but the Fahrenheit is actually based upon the human body. So 0 to 100 is supposed to be the temperature range that humans can inhabit. And so Fahrenheit is based more or calibrated more on the human body. So I always say if you ask what the temperature is outside, it's more useful to know it in Fahrenheit because you're asking about what it's going to feel to you. But if you're looking in a scientific endeavor, we need some reference to have common amongst us, and water is a fine reference, so Celsius is good. So why am I telling you this? I'm basically saying that people use different units and different measuring methods based upon what they're doing. So if you're going through your engineering career and you come up with a new terminology, or in particular a new measurement unit or a measurement scale, and it's foreign to you, it's likely because there's a different concept that you haven't encountered before, and the fact that there's a new measurement unit or scale is an indication that that is an easier way to understand this new concept. So instead of thinking I have to learn a new unit, you should be thinking about, this is a flag that something new is coming conceptually. And so dB is something that you've probably encountered before. dB is very useful to make comparisons for multiplication. And we use the log scale often because we can have signals that are as low as a picowatt or as high as a kilowatt in wireless systems. And so that's 10 to the 15th. So 15 orders of magnitude change in signal strength. So you can see with that kind of change using a logarithmic scale can be very helpful. And I just wanted to give you a quick reminder. If we do log base 10, by the way, everything we're going to do is base 10 unless I say otherwise, of x times y, and you probably already know that's simply going to be log of x plus log of y. By the way, this is how people used to do multiplication in the olden days. The slide rule would take the log of a number, and then you would add the two logs, and then you could take the inverse log and get the product. Just a couple other real quick ones. Log of 1 over x is simply minus log x. And then, of course, log of x to the n is n log x. Okay? dB is a logarithm based upon 10, and we write dB is simply 10 log 10 of the number. Now, we use 10 because in RF systems we're primarily dealing with power. In signals and systems you probably did a lot of work with 20 dB in 20 log, and that happens because those are voltages and currents rather than power. And the reason we're using the logarithms is because it's an easy way to do calculations. I do want to stop you here and just do a quick brain teaser. What is the log of x plus y? Think about this for a second. This is something that we will test a number of times and people often get stuck on. The log of x plus y is simply the log of x plus y. The key here is there is no simplification. Okay? It's when we multiply do we get this nice simple form. If we're adding, we don't. So to do this properly, what you'd actually have to do is add x and y in the linear domain and then take the log of that. And sometimes we might give you x and y in dB, and you would have to convert those to a linear domain and then take the log. So for instance, if, just do an example, x equals 3 dB and y equals 10 dB, All right, so I want to go through a couple examples. One of my colleagues put together a nice system of dB 1 through 10. So the log of 1 is just 0, so we get 0 dB. 1 dB is equivalent to 1.25 in the linear scale, and I'll just let you follow along. Pi over 2 is 2, 2 is 3 dB, 2.5 is 4, pi is 5. By the way, if you're wondering why pi is magically 5, please notice that these are approximations. We're just using pi because it's convenient and it's close. If you do this exact calculation, it's not exactly 5. So there's no magic here. It's just we all know pi is roughly 3.14 and it's easy to remember. 4 is 6, 5 is 7, 2 pi is 8, 8 is 9, that's kind of interesting, and then of course, final one, the log of 10 is simply 10. Now, this is kind of a fun exercise, but there's really only 3 numbers you need to remember, okay? 10 is 10 dB, that's easy to remember. 0 dB is 1. So 0 dB is the same as the same. What this means is if I take a signal and I multiply it by 1, I haven't done anything to it, so there's a 0 dB change. And 3 dB is the same as 2 times. And this is probably the most used one because we'll think about it. And it's pretty easy because 3 dB is twice, 6 dB is 4 times, and 9 dB is 8 times. So you can kind of move through this pretty quickly. So why are we dealing with power? Previously you probably looked at voltage and current because that's what you can measure with an oscilloscope probe or in a simulator, but why in wireless systems do we deal with power instead of voltage? And it turns out that it's kind of actually difficult to measure voltage and currents at high frequencies. And so what is easy to measure is power. So once again, this is going back to my sort of Celsius Fahrenheit. We're talking about power here because it turns out that's what we deal with mostly in the lab because that's what's easy to measure. There's voltage and currents is running around just like any circuit, but we talk about power because that's what's easiest to measure. The other aspect is that most signals are random. And it may sound a little confusing to you, but the carriers that we'll use, cosines and sines, they're not random. But the data we put on most communication signals is random. And the best way to think about that is if you're talking to your friend on the cell phone and you look at the bits that come out of it from your conversation, they're pretty random. And so if we're looking at a random signal, we can talk about its random properties. But the average power of that signal generally stays the same. So if I'm looking at your cell phone signal coming out, I probably can tell you exactly what its power is over the entire conversation. It'd be really tough unless I captured exactly all the data to figure out what exactly the voltage and currents were. So this is another reason why power is useful. And just a few things here. It's easy to measure. And the easiest way to measure power is actually just by putting the signal into a resistor and measuring its temperature. And that's actually how we do it. We actually have a resistor, we put the signal in and we measure the temperature change, and that'll tell us how much power was in that signal. And the only thing we need to know in the temperature change is what the value of the resistor is. And for convenience, we choose 50 ohms. And the reason why we choose 50 ohms is for the case of power, we could choose any resistance, but 50 is a number we choose once again because it's a useful impedance in the RF world. At home, if you remember the cables that would connect your TV to the cable television, they're coaxial cables, those generally come in 50 ohms and 75 ohms. It turns out that if you're going to build a coaxial cable, the highest power transfer, the most efficient power transfer would occur when that cable is 30 ohms, and the best voltage transfer would happen when that cable was 75 ohms. And when I mean 75 ohms, it's the characteristic impedance of the coaxial cable, which is a transmission line. We'll talk about that later. The reason I mention it now is, do we use 30? Do we use 50? Turns out 30 or 70. It turns out 50 is a nice approximation between the best power and the best voltage. And so that's generally why we have settled on 50 ohms as a standard for transmission lines. Because it's a standard for transmission lines, it's also the standard for instrumentation, and therefore we measure power in terms of 50 ohms. So there's a little bit of a background on why 50 ohms. And let's just look a little bit at how we would calculate power from voltages and currents. So, so when we actually do a lot of our design calculations, we're talking about voltages and currents. And when we talk about power, we have to assume that we're driving a 50 ohm load. And so when I ask you the power in a signal, I'm assuming it's driving a 50 ohm load unless I don't specify this. And this can lead to a lot of confusion because most papers don't even mention the fact that there's an assumption of 50 ohms. You just need to remember that. And so let's do a quick example. This is a low noise amplifier. It's basically an amplifier, and the output of the amplifier gives us a 632 millivolts. So this might be what you measure on an oscilloscope or in a simulator. And we want to know what the power of that signal is. Well, to calculate the power, you can think about this is just a buffer of 1 and putting it into a 50 ohm load and figuring out what the power of that would be. All right, so let's just look at this real quick. We've got 632 millivolts. Okay, so this is 1/2 of 632 millivolts. Okay, but that's the peak, right? Do you remember what the RMS is? The RMS is going to be 1 over the square root of 2 of that. Okay, and the power is simply equal to V squared RMS divided by R. So I'm going to take this and I'm going to square it, and I'm going to end up with 1/8. That's because I get a 2 from this and a 4 from this, times 632 squared divided by 50. And if you calculate that out, that's 998 milliwatts. Okay? And so if we're looking at a signal, we're assuming it's driving a 50 ohm. And so if I tell you the output of the LNA is 998 or about 1 watt, you could go and back calculate what the voltage is. And in fact, on a spectrum analyzer, if you want to know what the voltage coming in is, the spectrum analyzer is telling you what the power it's receiving is, and you just do the same calculation with 50 ohms to figure out what the actual power is. All right, so we talked a little bit about dB, and it was helpful when doing logarithms, but dB really is telling us a ratio. So when we say something is 10 times, we're saying, let's just take an example here. If I have an amplifier and I have P out and I have P in, if I say the gain is 10 dB, that means that P out over P in is equal to 10. Okay? So we're generally in dB dealing in ratios. In fact, we're always dealing in ratios. But sometimes we want an absolute value. And so what we're going to do is we're going to find an absolute value in power. I'll just skip through here. By defining a reference point. So for Celsius, we say water is a reference point. And for dBm, we simply use 1 millivolt as our reference point. And so what this means is that we basically say, what is the ratio of P out to 1 milliwatt, and that would give us dBm. Okay, so just as an example, 998 milliwatts. Okay, this is not an equal, it's a 10. So this would be 10 log base 10 of 998 milliwatts divided by 1 milliwatt, right? And so these would obviously cancel, and I'm going to take 10 log 10 of 998, and this is approximately equal to 10 log 10 of 10 to the 3, and this is equal to 30 dBm. Okay, so dBm is giving us an absolute power because we have an implied reference of 1 milliwatt, whereas dB is giving us a ratio, typically of a gain, and in wireless systems we're often talking about power, so it's a ratio of gain. It's important not to mix dB and dBm, and also when X is in dBm and it's amplified by Y dB gain, the final power is X plus Y dBm. Why is that? Well, imagine that I've got a signal coming in to an amplifier. Okay, if its power gain is Y and the input power is X dBm, the output power is going to be, if you will, sorry, let me erase that. The output power is simply going to be Y times X. Let's say Y was a factor of 10, then it would just be 10 times. And I want to stop you for a second and think about something a little bit different. What would happen if I had the output of two amplifiers, Y1 and Y2, and I now add them? I'm doing this contrast so you can see the two. Here we're multiplying, so we are adding. Sorry for that. We are adding our logs. Here we're adding in the linear domain. So what would the output be if Y1 and Y2 are in dB? Well, we're going to have Y1 dBm plus Y2 dBm. But remember, we can't, because the actual operation here is summation, what we have to do is we actually have to change this into Y1 linear. And so the way we would do that is I would say 10 Okay, now if we remember, dBm is 10 log 10 of P over 1 milliwatt. So what I would do is I would take Y1 and I would divide it by 10, and I would take all of that to the 10th power and multiply it by 1 milliwatt, and that gives me Y1 in linear, and I would add that to 10 to the power Y2, 10 times 1 milliwatt, and that would give me the linear power out here. So this would be P out in a linear. And if I wanted to put that back in dBm, I would just go back to this equation. So you can see that in multiplication, like for a gain stage, we're adding the dB, but whenever you're adding signals, you've got to go back into the linear domain. And we're going to test you on this several times because it's something that we often forget.